Howdy. We are a team of senior mechanical engineering students. We have been working on a particle plugging apparatus for Halliburton for the last few semesters, and are excited to share our work. Our project is in the field of petroleum engineering, and the apparatus we have designed will help test the characteristics of drilling mud on an oil rig. The project sponsor is Halliburton, one of the largest oil and gas services companies in the world. Drilling mud is a fluid that contains physical particles that are measured in microns. It is normally mixed on-site and pumped down into the well in order to hold back formation pressures, provide lubrication to the drill bit, and carry the drilled cuttings back to the surface. Its success in holding back formation pressure is dependent on how well it can plug pores that are in the formation. These pores can range from about 10 microns to about 2,000 microns in diameter. Geologists can approximate the size of these pores, but there has to be a mechanism to test the mud's ability to plug pores of the given size. Simply put, the particle distribution in the drilling mud must be tailored to the geological formation, and a mechanism to efficiently test its efficacy will enhance operational effectiveness. A particle plugging apparatus can test the performance of drilling mud. It does this by simulating a pore of a certain size, and running drilling mud through the cross-sectional area. If they are large enough and make up enough of the volume percentage of the mud, the particles will cause a blockage, or plug the cross-sectional area and not allow more mud to pass through. Some drilling fluids do not have particles large enough or in high enough concentrations to plug. Halliburton tasked us with designing an apparatus that could accomplish these tests in a precise manner. Requirements include that it needs to operate in real time, handle high pressures, and not be modular in design. A simple apparatus with minimal moving parts that could predict how a particular drilling mud would plug the pores in the formation.
The apparatus as designed fulfills all design requirements and constraints. These include the ability to operate under high pressure, be easily cleaned, operate and give results in real time, be adjustable with a high degree of precision, and successfully measure the pressure differential across the pore. To validate the design, a fundamental element analysis and flow simulation was run in SolidWorks. The design is built to be robust, and has a factor of safety of 25.
In the beginning of the project, multiple concepts were developed. The primary focuses of the design differences were the mechanism for adjusting the pore size and the cleaning mechanism. The final concept that was chosen is inspired by the shape of a snow cone. This conical section is inside of parallel walls, which has a cross-sectional area of concentric circles. The simulated pore size is the distance of the cone to the walls, and this distance is controlled by a high-precision linear actuator. Drilling fluid is pumped in at a constant flow rate by an external mechanism, and passes through the apparatus. There are pressure sensors on either side of the pore. The pressure differential that is measured across the pore will give information about whether the pore is plugged or not. Results can be seen and analyzed in real time. After the test is completed, a hose with pressurized air can be attached to the inlet to clean the apparatus.
As an alternative to building and testing the apparatus, the team built a model on Python that could simulate the particles passing through and plugging. This represented a shift toward computer science in the project. The goal changed from building a model and running tests to validating our design with a realistic computer model. The model takes various inputs, and its objective is to show how effective a certain particle distribution in the drilling mud is at plugging the pore. The way this was accomplished was by measuring the time it took to plug. The model inputs include the pore size to plug, particle distribution, flow rate through the apparatus, and the percent volume of the particles. The model we built uses randomly generated particles between the inner and outer radius. The particles plug when they form a chain from the inner to outer radius, as they can overlap slightly to mimic them touching as they flow through. They can also plug if they are generated on top of already existing particles on multiple quadrants. This model was built primarily with the constant flow equation, Bernoulli's equation, Cousiny-Kármán equation for permeability, and Darcy's law. Particles plugging the control volume decrease permeability of the cross-section because porosity decreases. With a few simplifying assumptions and using Bernoulli's equation, The velocity of the drilling fluid across the medium correlates linearly with the permeability of the cross-section. When the velocity decreases to a certain point that is close to the calculated velocity of 100% plugged, then the cross-section is classified as plugged. The final output of the model is how long it took for the particles to plug the cross-section. As you can see, we also built a graphical user interface and embedded graphs to demonstrate what exactly is going on. On top you can see a 2D visual of the cross-section, and on the bottom you can see a 3D visual of the control volume as the particles plug. The particles change colors once they are plugged. The outputs that make sense and are in line with what our Halliburton sponsors believed they would be in real life, and changing the inputs changes the output in a logical manner. With statistical analysis, the model outputs follow a normal distribution. The model has been optimized so that thousands of particles can be analyzed and they can be predictive of millions of particles that would actually pass in the real apparatus that was designed. The code will need to be tuned with real data to ensure its accuracy, but long-term the model may be as valuable as the actual apparatus design because it can be adjusted to model the interaction in seconds as opposed to 15 to 30 minutes per test with a physical apparatus.
Moving forward, the next steps of the project entail fabrication, integration, and testing. Halliburton will be able to use the design instructions to build the apparatus and test it out. This project's goal was proof of concept, and if the machine works as intended then Halliburton will be able to integrate it into the larger rig. Additionally, the Python model will be able to be fine-tuned as a predictive and useful model going forward.